Welcome back. This is going on to part question 5 now for Edexcel's S1 June 2012 paper. Now, given my crudely drawn frequency density graph here, what we've got is some policeman is wasting his life clearly watching the speeds of cars on a busy road at a 30-mile-per-hour speed limit. So obviously these people between 10 and 15 are, a danger. They should be shot, and so should the people doing past 35. But we don't live in a world governed by me, thankfully. Don't know why I'm saying thanks. Anyway, so we are told he was does something with 450 cars, so, recording the speed, nothing else. Anyway, so the histogram that we're given here represents results. Now, what I've done is I've sort of narrowed. I've obviously put the 450 cars, but I've also put 22.5 big squares. Now, these are just the squares that I've counted that are in here, and I can't really do any more than I could try and hold the exam this up to the camera and look like a right lunatic trying to point out where I've counted 22.5 big squares from. Or you could have counted little squares, but I haven't done that. Okay, so the reason I've done that is because we are asked in part A to calculate the number of cars that are exceeding the speed limit by at least 5 miles per hour in the sample. Now, as we don't know the frequency densities of each of these, all we know is the total amount of cars that have been surveyed or targeted, shot. So as I said, the only thing we can do is count the number of squares and work out what one square in terms of how many cars are in that one square, because that's essentially what we could work out if we have the frequency density. We want to work out how many. So what I've done is I've coloured the bars drawn the bars in green, rather conveniently, as though I know they were going to ask about this. Take that from what you want. It just shows I've done a bit of planning, but not too much. Anyway, go back to this. So we need to calculate the number of cars that were speeding at least 5 miles per hour over the speed limit in the sample. So this is kind of catching the people who aren't aware. Now, it's not all the cars that have passed the sample, otherwise we'd be including this 30 to 35 bar as well. We're just including the 35 to 40 and the 40 to 45. Now, I've done them separately, drawn them separately anyway, because A does it in the histogram that you're given, and we need to calculate them separately anyway, if you want to. Okay, so what you need to do, obviously, we've got 450 cars, and in 22.5 big squares, that area is equal to 450 cars. So we need to work out how much one square is equal to. So we just divide the 450 by 22.5. Okay, and if you would sub that in your calculator, you would get that as an answer that's equal to 20 cars. Okay. So we know one big square is equal to 20 cars. So we count the number of squares that are in the 35 to 40 and the 40 to 45, and times that by the number of cars in each big square, which is 20. Now, I've done this before, weirdly enough, and I've counted 4.5 squares. So as we know, each big square, so this big squares, counts as 20 cars. We do 20 times 4.5. and we get an answer of 90 cars. Okay, so there are 90 cars that are speeding, so 90 out of the 450 cars that are speeding over 5 miles an hour above the speed limit. Now the next part is estimate the mean speed of the cars in the sample. So what we've got to do here is work out how many cars we're going between this. Now, because we don't know the individual speeds of the cars, we just know that between 10 and 15 there were X amount of cars. So between 10 and 15 miles per hour there were X amount of cars in there. Now, we just do the logical thing and assume that they were all going at 12.5 metres per second, or whatever this is registered in. Just a speed of car, but I like to be physical in terms of the units way, not the other way. So anyway, we assume just they're all 12.5, because obviously some are going to be above that, some are going to be below that, so we take an average. Alright, so we assume all of them are halfway between, so that'd be 12.5, that'd be 25, that'd be 32.5, that'd be 37.5, and that'd be 42.5, etc. Alright? Why did I say etc? I've given you all the different speeds. So you work out how many cars, because we worked out how many squares, so we know the 22.5 big squares and the 450 cars, so each square is worth 20 cars. So you work out how many cars are in each band in terms of the group, and you times that by the median speed, so you can work out how fast all of the cars are going, and you divide that by the number of cars. So basically what I'm saying here is the mean, okay, is 12.5 times 30, because there are 30 cars in a 10 to 15. Obviously you would work out how many squares are in the 10 to 15 bracket and times it by 12.5. So I worked out there were 30 cars in there. So we know each square is worth 20 cars. So obviously that's 1.5 squares. Doesn't take a genius to work that one out. So what that does really. So anyway, usually count the number of big squares in each thing, or small squares, squares, and you can work out how many cars are going, and we all assume the cars to be going halfway between the two extremes. So plus 240 times 25 plus 90 times 32.5 plus 30 times 37.5. I mean, I'm sure you can work out just from what numbers I'm putting down how many squares are each one in. Sorry, how many big squares are in each frequency group. But I'll explain it anyway for those that you can't be bothered trying to work it out. But it just means obviously I've got to do more work. So 60 times 42.5, and that is up. You're all over 450. Okay, so obviously, as I said, in the first one we've got 1.5 squares, because we've got an answer of 30, which is, say, if 1 square equals 20, then obviously we've got 1.5 squares is going to equal 30, and then 240. So I'm just working this out what I did, because I've got so we've got 12. Is it that many? Yeah, we've got, because I've drawn this to scale, so it's a bit thicker than that. So we've got, basically we've got, I probably should write this down actually. So we've got 1.5 big squares in the first group, in the 10 to 15 group, and in the 20 to 30 group we've got 240. Oh, sorry, not 240 squares, we've got 12 squares. And in the next group, sorry, let me just see where I've gone working from here. Sorry, we've got 3.5 squares in the next one, and then we've got in the one after that, so we've got 1.5 squares, and then 40 to 45 group, we've got 3 squares. Okay. Now the reason we don't just add all them numbers up, the 1.5 to 12, 3.5 to 1.5 and the 3 and times it by 20 is because, well, we've got to work out the individual speeds of each of these cars. It's sort of like a momentum thing. You can almost think of it like that. But then again, that might just confuse you. Alright, so hopefully that's made some kind of sense. Now the next part requires a bit of interpolation. So part C says, estimate to one decimal place the value of the median speed of the cars in the sample. Now it's the median, not the mean. So we're looking at the one halfway through these number of squares. Now we know there are 450 cars in this sample. So you divide 450 by 2, you get 225. You hopefully you've worked out how many cars are in each sample, because I've kind of told you. So it's 30, 240, 90, 30 and 60. So you add them up and you find the median lies in the group that's 20 to 30, and it lies 195 into that group. So there's 195 cars into this 20 to 30 group. So the bottom is 20, that's plus the number of spaces into the group, 195, over the total in the group, which we know is 240, times the width of the group, which is 10. Now, this is not 11 because they are evenly spread out. So the ending of this one is 30 and the starting of the next one is 30. So there's no missing out there. So we don't have to add another one onto each side of it. Okay? So basically that's the standard interpolation formula of you add the bottom value, the range, you add that to the brackets, the number of spaces into the range over the spaces in the range times the width. So if you think about it, this is quite logical. You could have come up with that formula. It doesn't take a genius of a mathematician to work that one out. So even if you forgot that, it's just saying, okay, so obviously if that was 240 into that group, you'd assume it to be somewhere near the end of it. Alright? So anyway, that's time for a different video. So that gets you 28.185. 125, sorry. Or you could round that to 28, it said is acceptable. Now, keep your eye on the mean. Sorry, the mean I didn't work it out for you, that was 28. Alright. Next question, part D. Comment on the shape of the distribution. So, the shape of the distribution, so in terms of it's positively skewed or negatively skewed, that kind of thing, is it? What's the kind of spread look like? Now, reading up on the answers, they did allow two separate answers, and that's because this 20.125 and this 28 are very close, and you could round that to 28 if you wanted to. And that is why in the answer there's two answers. One of them says there's no, it's an even symmetrical graph or distribution because the mean is very close to the median, so the mean is in the middle. So obviously if the mean is in the middle, then the quartiles, the upper quartile and the lower quartile are going to be the same distance from the median. And that's how you work out the skewness, by looking at two distances, one between the median and the upper quartile and the other between the median and the lower quartile. But as these are very close together, obviously when you half this and add it on or take it away, you're going to get very close numbers, either using the mean or the median. So that's one answer that could have been accepted. However, the main one they wanted was said as the median, which is as the median is greater than the mean, there is a positive skew, but an only very marginal skew. The one they were looking for is a positive skew, but you could have said it is symmetrical because they are so close together. So the distance between the upper quartile and the median and the lower quartile are the same, or the mean. Okay, so as I said, hopefully that's been able to help you. Do apologise, but that's why there's two different answers on the mark scheme. So I do think it's quite a tricky one, that. So you might have come out of the exam in that year and thought, oh God, or been doing this paper and thought, oh, why does it say an answer and I've got something different? So I've tried to explain why they've given both answers on there. And also, as always, well done for making it through this video. You don't get many revision channels that say that often, do you? But not many of them are as boring as me. So anyway, thanks for watching, and we'll see you in the next video. As he says rather happily. Alright, I did just forget to add a little bit there to that question 5. On my exam sheet there's a party over the page, so I think I just wanted to get rid of question 5 as quickly as I could, to be honest. Anyway, 5A, so I do apologise. Hopefully I'll try and cut that little bit out, but still I'm explaining it now, so why bother, hey? Anyway, 5E says, state with a reason whether the estimate of the mean or the median is a better representation of the average speed on the road. Now, basically, the way to think about this is we use the mean to get an kind of average, whereas the median is the one in the middle. So which one do we use? Which one gives us a more accurate representation of where the middle really is? Because obviously we were assuming these speeds, so the median, the mean or the median might not be correct. One of them is going to be different. Now, as it's skewed, that gives us a clear indication of which to use. If it was symmetrical, then we'd say the mean, sure, because the mean says an average, so it surely should be in the middle. Whereas the median is always a bit more, because it's skewed, the median is skewed with it, whereas the mean isn't as much affected by a certain level of skew. As long as the range is the same, having more values at one end doesn't really affect the mean, whereas it does the median. So therefore, because it's skewed, the median gives us a better idea of what the shape of the distribution of the data looks like. Okay, so that's why we say the median, not the mean. So sorry about that, I just obviously missed that bit out, but hopefully that doesn't happen again in another question.